All right, so we'll go ahead and get started just so we can stay on time and have plenty of opportunity for questions. Our first speaker is Dr. Bulent Coach with Clemson University, and he's going to talk about mechanizing the removal of soil between peach trees planted on berms. I'll show you where your, there's your pointer.
Okay, great, thank you. Thank you, Sarah. Good morning. I'm Bulent Coach. I'm a faculty member at Clemson University's Agricultural Mechanization and Business program. And the title of this presentation is Mechanizing the Removal of Soil Between Peach Trees Planted on Berms. Just to show you the outline, I'll briefly talk about the armillaria root rot disease and the methods that have been tried to control this disease. And this presentation is related to the cultural methods, which is related to the above ground root collar excavation. And then I'll briefly mention the objectives and the machine that we are retrofitting to remove the berms between peach trees that are planted on berms. Then we have done some field experiments. I'll talk about those two, and finally conclude with the results and the summary of the presentation. This is part of a multi-state grant funded by the USDA, Solutions to the Armillaria Root Rot Affecting the U.S. Stone Industry. That's led by Dr. Ksenia Gasik and several other people from 4 or 5 different states. So armillaria root rot is a fungal disease. It would affect the stone fruit, and that is one of the major cause of tree decline and losses in peaches in the southeastern United States. Once the tree roots are infected by this armillaria, different types of armillaria species would cause this disease, then the fungus would move upward towards the root collar area of the trees, and that would be creating a white fan-shaped layer, and that would girdle the tree, and that would cause the tree decline. Several methods have been investigated and tried to control this disease. Chemical and biological methods include using the fungicides and some other chemicals to sterile the soil and try to mitigate this problem. However, currently there is no economic solution using chemicals to control this disease. Genetic methods would involve development of rootstocks that would be resistant to armillaria. That's also under development. And this multi-state grant, one of the objectives is working towards that. And the other method is the cultural methods, changing the way the production is taking place. So for example, planting the trees on berms and executing above ground root collar excavation would be helping to suppress or delay the progression of the armillaria, and that would extend the economic life of trees. That might also help reduce the spread of the disease into other trees. Above ground planting trees on berms. Studies have been done by Dr. Guido Schnabel from Clemson University on peaches, and he has been doing this kind of work since 2012, and he's one of the collaborators of this project that I'm presenting. Also, Cole Scruggs, he was the master's student. He worked with us over the past couple of years on this project. So as I mentioned, root collar excavation would be one of the methods that would require the removal of soil around the bottom of the tree, the root collar area, and exposing those upper roots to the weather conditions, hot and dry or cold weather conditions, along with sunlight, that would be keeping the progression of the disease, and that helps reducing the progression. Root collar excavation can be done on trees that are planted on the soil level. However, because it requires removal of some soil around the tree trunk, over time the wind and rain might be bringing the soil and filling those areas. So in that case, that would require periodic root collar excavation. To conduct only one root collar excavation, that's why the berms are created and trees are planted on those berms. After 2 to 3 years of planting, then the root collar excavation would be executed, and because the trees are slightly elevated, then we wouldn't be getting the tree trunk areas filled with soil. In order to plant the trees on berms, we need to create berms. Berms can be created in the sizes of about 1.5 foot tall and about 3 feet wide. Depending on the type of machine used, different producers might be coming up different berm sizes. In order to do some of the subsequent operations on berms, probably it would be better to have standard berms on a field. And the equipment that are used to create berms includes a scrape blade or a modified AMCO LF6. As you see on the top image, that is the scrape blade. It's pulled behind the tractor at an angle on each side of row. That's how the soil is being pulled and a berm is created. And the second machine is the modified levy plow. This levy plow is at Clemson University's Musser Fruit Research Farm. And as can be seen, there are discs on each side. So a berm can be formed with just one pass. And between the discs, there is a roller on the top. So the soil that is brought to the center, and that roller would apply some pressure to compress the soil. In order to have good contact between the tree roots and the soil, some compaction would be needed. So this roller would help providing that compaction. Then the trees would be planted, and after 2 to 3 years of planting, the tree roots would be developed and it would be established on the soil. Then we would conduct the above ground root collar excavation using hand tools and compressed air. You see in this case an air spade is being used to clear the soil. That air is provided by a compressor that's pulled behind a tractor. On the top right image, you see a tree with above ground root collar excavation. You see the top parts of the tree roots are exposed to the sunlight, to the hot and dry environment, and that's how the armillaria fungi is being stopped and the tree life is extended. Having berms have several advantages, such as it lets to facilitate the root collar excavation, and it reduces the likelihood of runoff or other natural events filling in exposed root collar after the root collar excavation. Letting the trees to grow 2 to 3 years allow roots to establish, And heating and drying of soil provides less ideal environment for the armillaria. Despite all these advantages, berms might also cause some disadvantages as well. For example, berms may channel water under heavy rainfall. It would create or increase the runoff, and it might cause excessive soil loss from the orchards. It would create pools of standing water in certain areas where the drainage is not good. So the berms would block the water flow, and that might create pooling of water. And that would also decrease the worker comfort and safety in field operations, such as during thinning, pruning, or harvesting operations. The crew members need to walk up and down of those berms. So because of these disadvantages, some producers might use different tools to knock down the berms, such as using hand shovels or other tools that might be time-consuming and labor-intensive. Some of them tries using a front-end loader or skid steer to bring the or knock down the berms and spread the soil onto the orchard floor. However, the maneuvering this type of machine within an orchard might cause damage to the trees. Or some producer would just leave the berms alone in the field, so they may not do anything. So the objective of our study here is to come up with a mechanism that would knock down the soil between the trees, and just to leave a soil island around the tree trunk that might help later operations such as the above ground root collar excavation a little bit easier maybe. In order to do so, we wanted to integrate some sensors, and we wanted to test this machine in field conditions to find out how the machine is operating and what operating conditions would be helpful for the process. And we also wanted to see how well the machine is knocking down the berms and creating a smooth orchard floor. For this purpose, we used a John Deere 5101 EN tractor. It has 99 horsepower engine horsepower and 82 PTO horsepower. So the tractor was big enough for the machine that we are going to be operating. On the right side of the image, you see the hydraulic circuit animation. This is relatively simplified version that we came up with. The machine has a power source, which is a hydraulic pump that is driven by the tractor's PTO shaft. And we have a hydraulic motor that would be driving the paddle wheel that I'll be talking about in a few minutes. And we have a hydraulic cylinder that would be extending and retracting the paddle wheel and the hydraulic motor assembly. We have also included some transducers to monitor the machine operation. The locations of those transducers, one flow meter that we included at the inlet line of the hydraulic motor, and we had two pressure transducers we included in the inlet and outlet of the hydraulic motor. With the help of the flow meter, we can determine the paddle wheel's RPM, the speed during its operation in the field. With the help of the pressure transducers, we can determine how much torque is required under different soil conditions. So the idea was to monitor those as we are doing the operation. To collect the signals from those transducers, we came up with a data acquisition system using a microcontroller. In this case, we used Arduino Mega, and we have also used some radio transmitters so that the data can be transmitted wirelessly to a laptop, either in the tractor cabin or outside, away from the tractor. The machine that we retrofitted is a Weed Badger. It's commercially available. I believe the company may not be in business right now, but their machines are still available. The used ones can be purchased online or from different auctions. So the machine was the Weed Badger 2030 model, and it came with a hydraulic pump. We replaced the hydraulic pump on that old machine with a 21 gallons per minute PTO-driven pump. It had a hydraulic motor with a 17 cubic inches per revolution displacement. We have also replaced that. We also replaced pretty much all the hydraulic lines on the machine. And it came with a pressure relief valve and a flow control valve, so it was allowing us to manually set the flow rate of the hydraulic fluid going into the hydraulic motor. This machine would withstand up to 3,000 psi. We have also used an RTK GPS receiver so that we can determine the GPS coordinates and determine the tractor's ground speed based on the RTK GPS. For this purpose, we used MLID Reach M2 rover station and RS2 ground station. On top of the cabin you see here is the rover, and we had a base station away from the tractor on the corner of the field. And here is the flow meter that I mentioned earlier. It has a display unit, and it can also transmit the flow rate signals to the data acquisition board as well. We used McNaught MX19F for this purpose. The pressure transducers, we used Cartech pressure transducers. These transducers provide signals between 0.5 volts to 4.5 volts. That is corresponding to the pressure rates between 0 and 3,000 psi. Here is one of the transducer that's at the inlet line of the motor, and the other one is here with an angle here. So that's on the outlet side. We came up with a wireless data transmission, as I mentioned before. So one of the graduate students with the laptop was capturing the data on his laptop. We had a Python script and C++ code to capture the signals from the pressure transducer and flow meter and combine that data with the GPS, RTK GPS data. We have also used a UAV and a camera platform to take aerial images of the orchard that we tried our machine. For this purpose, we used a DJI Mavic Pro equipped with a MAP IR RGB camera. We flew the UAV at about 110 feet above the ground with 75% image overlaps over the orchard, and all the data or the images that was collected with the camera were processed using Edgesoft MetaShape. We used structure from motion to come up with the digital elevation model, and ArcGIS Pro and Microsoft Excel for data analysis and processing. So these are the three different designs of the paddle wheel that we came up with, and we attached it to the hydraulic motor. The first one has the dimensions of 10.2 centimeter and 20.3 centimeters. That's the pedal length, 20.3 centimeters, and design 2 and design 3. The reasons we had those 3 different designs were based on our experiments. Once we realize or do the testing and see that the pedal wheel size is not tall enough or it's not wide enough, then we had to go and increase the dimensions to serve for that berm. So for this experiments, before we take the pedal wheel and the machine to the producer's field, we did some preliminary experiments. We created the berms using a berm plow, and we tested the pedal wheels. All those preliminary testings included the ground speed levels and the RPM levels of the pedal wheels. So based on those preliminary tests, we came up with 3 different ground speeds and 3 different RPMs that we wanted to operate the machine at the commercial field. The field tests were conducted at the Hyder's farm in Campobello, South Carolina. We appreciate their help and opening up their orchard for testing the machine. The fields, the orchards had 2 to 6% slopes. Predominantly, they had the sandy loam soil in those fields. And here is the first test that we had. So we tried the pedal wheel design 2 for these tests. And with the 3 ground speeds and 3 RPM levels, we came up with 9 combinations of those values, and then we replicated those 3 times. So here is the orchard. This is how we came up with the different zones. And within each zone, we visually assess how well the berms are being knocked down. And we have also used the aerial images before and after that I'll be showing in a few minutes. And this is the field for the second trial. After doing the first test, we realized that the pedal wheel dimensions is not large enough to knock down the berms with 2 passes. So it was leaving some small ridge in the middle. So we went ahead and designed the third design that I just showed. Here is a short clip of the testing on the first trial. As you can see, a narrow ridge is being left after 2 passes in the middle. This was due to the berms, the berm size that I mentioned earlier. Some areas were slightly larger width. That's why with 2 passes we weren't able to cover the whole thing. However, this is basically the floor after knocking down the berms. As you can see, the pedal wheel is spreading the soil pretty nicely and creating a smoother surface right after, and it leaves a soil island around the tree trunk. As I mentioned before, it might help facilitating the above ground root collar excavation a little bit easier. And these images are from the second trial location. That second orchard where we tested the machine had a lot of weeds, whereas the first one didn't have any weeds. So because of the weeds that are shown on the berms, it was creating a lot of stalling. So the operator, the graduate student who was operating the tractor, he was also making notes of those stalls as well. So with the weeds, we needed to operate the pedal wheel at much higher RPM so that we would get over those conditions. This is just a short clip, and this is another one. So because we were able to test two different pedal wheel designs, we were able to compare the torque requirements. As I said, the second field had a lot of weeds on the berms, so it required much higher torque than the pedal wheel design 2, the previous orchard. And we had also more stalls on the second field. As you look at day 1 indicates the first orchard trial, and day 2 is the second orchard trial. So the pedal wheel stalled more frequently on the second field because of the weeds that you see here in this image. So with the testing that we conducted, the pedal size depends on the size of the berms. So we need to come up with the length of the pedals depending on what berm widths that we have. High rotational RPM of the pedal wheel consistently provided lower torque, which makes sense if you operate faster RPM, then each pedal is taking a small amount of soil at every pass. So it's not facing large amounts of soil, so that requires less torque. But if you increase the RPM too much, then you might be spreading the soil too far. And if you have some rocks in your soil, those rocks would be going like a bullet. So you might need to pay attention to those as well. And the ground speeds, depending on the operator experience and the field conditions, can be set. But we came up with 1.8 miles per hour and 177 RPM seems to be the operating conditions for knocking down the berms. Briefly, just to touch base on the cost of this machine, we spent about $2,900 for the used Weed Badger. We have been looking for these old machines. You can find anywhere from $900 to $6,000. By the way, Weed Badger is not the only company. There are other companies coming up with similar mechanical or organic weeding machines. So those machines probably can be retrofitted as well for this process. The pedal wheel 3 design, we spent about $736. That depends on the metal prices and the labor. Everything is going up nowadays, so it might be going up to $800 to $1,000. So in total, with the used equipment, the bermer, the machine that I have talked about so far, would cost about $4,000. Here is the aerial image that we have taken with the UAV. These darker areas are the shades of the trees. This image was taken in the morning, and you can see the berms visible onto these images. This is before the deberming operation, and this one is the after deberming operation. As you can see, the shades are on the other side now. And from these images, you can see that some thin, narrow ridges are left because the width of the machine wasn't large enough from our first trial. So these aerial images helped us to see how well the machine is smoothing the surface and knocking down the berms. With that, we continue working on improvements on the machine. We are intending to add some sensors to detect the tree trunks. So the extension and retraction of the pedal wheel was done manually by the operator. We would like to have sensors integrated so that the operator doesn't have to pay attention to that. We would also like to add an electronic flow control valve so that the operator can adjust the flow rate and the RPM of the pedal wheel from the tractor cabin rather than manually getting out and setting the flow rate. We would also try to see different brush mechanisms to see if we can help facilitating the above ground root collar excavation with a machine, something like this. So that's all I have for this presentation. I would be happy to hear any comments or questions that you might have. Thank you.
Don't be shy.
Did you assess root damage?
Actually, when we started working on this machine, the idea was to use a similar machine to do the root collar excavation. And we have observed some root damage. So that's why we kind of pulled back and we went ahead and did the berming between the trees. We wanted to leave the island around the tree. But with this machine, we didn't see much damage on the roots. I have observed only one of them, and the roots were just, would be anywhere under the tree, but one or two slight damages that we have observed. Any other comments? Yes, sir.
How close to the trunk? How close it goes to the trunk?
It's about 80 centimeters that we would like to get close. So 80 centimeter radius would be the area that we leave.
Have you estimated the cost of the other changes you'd like to make to the machine?
It will be like one of the major cost items that I mentioned here is the RTK receiver. You may not need the RTK receiver, which is about $3,000 we had to add on. The other ones will be about $1,500 to $2,000 at the most. The other changes that we would make on the machine. Yes, sir.
Have you compared this tree and debermed it with the tree without? Have you compared this tree which you debermed under the tree?
We haven't done that. We just did the deberming operation. One test we did in October 2021. The other one was in 2022. So we took some images from the first trial. Those ridges were still there, the little thin ridges. But over time with the rain, probably they will be flattened too. Yes, sir.
Roughly how much percent there was decline in the disease after this berming and root collar excavation?
We haven't looked at that, but again, the idea is doing the above ground root collar excavation. So without root collar excavation, probably we will not be able to keep the fungus in the soil. So here we didn't come close enough to the trees to do the root collar excavation. We just knocked down the berms between the trees. But others might be able to answer that question. I'm an agricultural engineer, machinery engineer. It's not my area, unfortunately.
It shows that the life of the trees is extended if you do the root collar excavation. With the standard rootstocks and practices that growers do, it extends for several years. But it's the time that we are still evaluating those fields, and we'll see how long. At the time that we published the paper, it was 8 years, I think, and that was significantly lesser on the trees in the hot spots that were planted on berms and root collar excavated versus the one that were planted just on the flat, like summer.
Anything else?
I appreciate everybody's questions. Thank you, Dr. Coach.
Thank you.